My name is Wallace Moreira Bessa, and since March 1st, 2021, I have been an associate professor of mechanical engineering at the University of Turku. Here, at the University of Turku, I am engaged in both teaching and research in smart systems, robotics and mechatronics. Today I'm going to talk about my research on intelligent control of mechatronic systems, which is actually a very essential part in the development of smart devices. Well, before showing some results of my research, I will try to answer two fundamental questions. The first one, what is intelligent control? I mean, how can we tell it apart from, let me say, other conventional control schemes? And the second one, when do we need intelligent control? That is, what are the advantages of this approach? After that, I will show you some applications of the intelligent controllers that my colleagues and I have been able to design and implement so far. So let me start by talking a little bit about control systems. Suppose you have an industrial robot and you want it to perform a given task. In this case, the robot needs to perform a desired motion that we usually call the reference. The controller, by means of sensors, constantly monitors the robot's motion and compares it with the reference. Based on this difference, which we call error, the controller defines the electrical signals that should be sent to the robot's motors in order to allow the desired motion to be performed. That's how the trick works. But let's take a look at this specific case. This type of robot usually works in what we call a well-structured environment. It performs repetitive tasks, protected in a cage, without interacting with humans, and with almost no disturbances at all. I mean, here everything is well known, and there's no space for the element of surprise. Now, let's compare to what happens with Stretch, the new mobile handling robot for warehouses from Boston Dynamics. The robot will need to cooperate with humans and other robots as well. The cargo weight may vary widely. It means that uncertainties and external disturbances will be very common. Thus, in this case, conventional control schemes with fixed gains may fail to provide the required performance. In this case, a more appealing solution would be the adoption of an intelligent compensation scheme within the control law to recognize and previously compensate for uncertainties and external disturbances that can arise. But in order to design an intelligent controller, first we need to understand what intelligence is. Unfortunately, there's no consensus about that. According to Rudolf Pintner, intelligence is the ability to adapt oneself adequately to relatively new situations in life. Walter Dearborn, on the other hand, stated that it is the capacity to learn or to profit by experience. And recently, the neuroscientist Rodolfo Linhares claimed that prediction is the ultimate function of the brain. Let me now try to put it within the control systems framework in order to highlight the required features of an intelligent controller. The controller must be able to adapt itself to changes in the plant. It should learn from experience and acquire knowledge by interacting with the environment. Adaptation and learning allow the controller to improve its ability to make better predictions about plant dynamics and to improve the overall control performance as well. And how can the controller achieve these learning, adaptive and predictive features? Artificial neural networks or other machine learning algorithms can be embedded into the controller for this purpose. Here, for example, we have a single hidden layer network that is fast enough to be used in real-time controllers and can be easily deployed in edge devices. It has been analytically proven that such a neural network can perform universal approximation. As an universal approximator, it can approximate any function with a desired degree of accuracy. On this basis, it can be used to recognize and previously compensate for uncertainties and external disturbances that can arise. It should be highlighted that learning requires memory in order to remember and to repeat the successful control actions. In fact, during the learning process, the synapses, the digital synapses of this artificial neural network are constantly adjusted and stored in this weight vector. Moreover, learning can be performed either offline by means of a pseudo-inverse or online using an adaptation law. But is machine learning alone enough? I would say that there are several control methods that can be combined with machine learning to improve the overall control performance and to ensure robustness as well. In my research group, we usually take advantage of the nonlinear control theory to design our intelligent schemes. By means of the Lyapunov stability theory, we don't need to linearize the plant, which allow our controllers to deal with a wide operating range. Sliding mode control, for example, can be easily combined with artificial neural networks and other machine learning algorithms to implement an intelligent controller. Sliding mode theory was conceived and developed in the former Soviet Union. The main idea behind the method is to transform an nth-order trajectory tracking into a first-order stabilization problem. This can be achieved by defining a stable manifold, the so-called sliding surface, and a control law to ensure the convergence of the tracking error to this surface. Once on the manifold, after the reaching phase, the sliding mode takes place and the error exponentially converges to zero. Here, in the case of a second-order system, the sliding surface is a straight line. For a third-order system, it's a plane. For a fourth order, a hyperplane, and so on. So, the control law and the gain should be developed in order to achieve the so-called sliding condition, which is a Lyapunov-like stability criterion that ensures the sliding surface attractiveness. But a known drawback of conventional sliding mode controllers is the so-called chattering phenomena, due to the discontinuous term in the control law. In the case of mechanical systems, chattering should be avoided because it can excite higher vibration modes. In order to avoid undesired chattering effects, a thin boundary layer neighboring the switching surface may be adopted by smoothing out the sine function. This can eliminate chattering, but spoils the tracking performance, which in fact means that a steady-state error will always remain. In order to overcome this major drawback, a few years ago, I have proved that actually the error converges to a closed bounded region. I don't want to bother you with the mathematical details of the proof, but the first part relies on a Lyapunov-like stability analysis, and the second one on the solution of a set of differential inequalities. It means that now we can propose our intelligent compensation scheme within this convergence region without compromising the overall system stability. And when do we need intelligent controllers? I know that many control engineers and many companies use conventional controllers like PID, for example, and in fact, you can still use it for many applications. However, with the expansion of the fourth industrial revolution, the demand for more embedded intelligence tends to increase. And it happens because when interacting with us, these devices work in an unstructured environment and are subject to uncertainties and external disturbances. Mobile robots, for instance, may bump into other objects and even into humans, which of course we need to avoid. In addition, since users are typically different, devices need to learn and to adapt themselves to each individual. Before introducing some obtained results, let me show you a brief comparison between a conventional and an intelligent controller. For example, let's compare a PID controller to an intelligent scheme designed as a neural network embedded in a sliding mode controller. First of all, I would like to highlight that the operating range of our intelligent controllers is much wider. Since the entire controller design is based on nonlinear theory, the intelligent scheme is not limited to work in the neighborhood of a set point. Tuning the control parameters in both cases is easy and straightforward. From the point of view of the final user, I mean the person that will tune the controller, the size of the parameter set in both cases are also comparable. Finally, the intelligent controller can ensure robustness over a wide operating range, which cannot be achieved using PID control. Let me now show you some applications with intelligent control. The first one is the intelligent control of a mobile robot. In order to provide the adaptive, learning, and predictive features, the controller was designed as a nonlinear scheme with an artificial neural network embedded in it. The main task is to follow a previously defined trajectory as the circular path in this graphic. We have assumed that we know the dynamics of the robot, but we don't have any knowledge about the friction between the wheels and the floor. Friction is not so easy to model, and it depends a lot on the surfaces involved. By assuming no prior knowledge, the robot is able to navigate on different types of floors. As we can see in the graph, due to the ability of the artificial neural network to identify and to compensate for friction, the intelligent controller, the blue line, shows a much improved performance and allows the robot to track the desired circular path, the dashed line. The conventional controller, the red line, fails to track the path, as we can see. Together with my colleagues of the Hamburg University of Technology, we have applied the intelligent controller to an overhead container crane. This is a typical underactuated mechanical system, and we have assumed we don't know exactly the cargo weight. Here, for example, the container should track a desired path without oscillating in order to avoid an obstacle. And once again, we can see the much improved performance of the intelligent controller in the blue line. The conventional controller, the red line, wasn't able to cope with a task when the system is subject to a high level of uncertainties. And we have also applied a similar scheme for the intelligent control of underwater robots. In this case, the learning feature is essential for the controller, because the intelligent scheme should be able to learn about the hydrodynamic effects, the added mass, the hydrodynamic damping, in order to compensate for it. I specially selected this application to show you that our intelligent controllers don't need a powerful hardware and can be easily deployed in tiny microcontrollers. Devices like that can be used to explore ocean phenomena or even inside industrial tanks for monitoring chemical processes. The next application I would like to show you is the intelligent control of an electrohydraulic actuator. Electrohydraulic systems are widely employed in robotics and automation. They are able to keep the load capacity without heating. That's what happens with electric motors. This is, of course, a nice application, but actually, I included this slide to emphasize the difference between adaptive and intelligent control. An adaptive controller has no memory, so it always needs to adapt, even if it has already experienced the same situation before. An intelligent controller, on the other hand, is able to learn by experience, providing an improved performance with less effort. I would also like to show an ongoing research that is being carried out in cooperation with the Federal University of Rio Grande do Norte. Our goal is to propose a reliable controller for an artificial pancreas, and it must be able to deal with all intrinsic uncertainties of this type of problem. Intelligent control has a huge potential to be deployed in smart healthcare devices like that. As we are not machines, our body dynamics is very uncertain, which poses a perfect scenario for the application of intelligent control schemes. We are still at the beginning of this research, but the obtained results so far are very promising. Finally, what about my future research perspectives? In addition to my research on intelligent control of mechatronic systems, I'm also very interested in the application of machine learning to smart condition monitoring and to predictive maintenance. According to McKinsey & Company, for example, predictive maintenance typically reduces machine downtime by 30 to 50% and increases machine life by 20 to 40%. Considering that the price of smart sensors and edge devices has dropped dramatically in recent years, smart condition monitoring and predictive maintenance have the ability to increase companies' productivity and competitiveness. This is something that I want to start investigating here in Turku, and maybe we can do it together with your company. So that's what I would like to show you today. If I succeed to draw your attention to the advantages of intelligent control or to any specific application and you want more information, please do not hesitate to contact me. Thank you very much for your attention.